Hello, my name is Jonathan Sunday. I'm Strato's Chief Engineer for Draft Systems, and we're here today to talk about the evolution of freight rail energy management systems. The North American freight rail network is an undeniably mature industry, with the first railroad charter granted in 1815, first steam locomotive in 1826. We're just going to discuss the past century or so, where trains have grown longer, heavier, and faster to meet the needs of the continent. As with anything, the inevitability of change has transformed the railroads over this time to match the demands on the system. As the industry has developed and expanded, the operators have managed to balance this development to maintain an ingenious continuity between the established equipment and infrastructure investments and the evolving expectations placed upon them. These longer, heavier, faster trains generate a large amount of energy that must be managed in the opposing environments of yard impacts and over-the-road revenue service. In the decades around the turn of the last century, the railroads were in a transitionary phase. The fleet of wooden cars was gradually being replaced by heavier and higher capacity steel construction. The Railroad Safety Appliance Act of 1893 mandated the removal of all hazardous link and pin couplers by 1900. These were upgraded to modern automatic couplers, alongside the implementation of air brakes on all cars. The single-spring energy management equipment of the wooden car era was no longer adequate as the fleet changed over to steel. So the tandem spring arrangement provided protection until cars were strong enough for friction draft gear. The term draft gear is originally a collective plural describing all the stuff that went into the end of the car. Friction draft gear was the standard energy management system going into the 1920s. Most of the energy capacity of these systems is generated by the friction of steel plates being forced against the outer housing, with a set of internal steel springs only serving to return the unit back to its neutral position. When the unit is compressed, the higher forces shown on the red curve are the result of the sacrificial plates in this friction clutch, as compared to the much lower release curve representing the coil springs alone. The bounces in the compressive stroke show the stick-slip phenomenon as these plates catch on each other and successively break free again until the unit is collapsed. The wearing in of the friction clutch is what causes the draft gear to lose energy capacity as it ages. The curve as a whole is produced by dropping a 27,000-pound weight on a draft gear from higher and higher positions until it collapses. Though a total force of 500,000 pounds was generated in the highest level drop, you can see on the chart that it didn't take but 250,000 for the gear to actually collapse. The first friction draft gear was originally tested in 1887, proving that this new system would allow train lengths to be doubled to 50 cars, though the $30 units were too expensive and too stiff to be effective on the lighter wooden $600 cars at the time. The M901E drop hammer curve on the previous page looks very different from a curve generated by impacting cars together. The first phase of the curve runs out the half-inch or so of free slack in the system before the force levels overcome the friction clutch and the gear strokes with little resistance. A second larger impact is felt as the unit goes solid at the end of its available travel. This is shown in the impact video as the pressure of the incoming hammer car momentarily builds before any draft gear deflection can be seen. Eventually, a different specification was written governing the impact performance of the M901G class of draft gears. This requires a maximum reaction force of 500,000 pounds when impacting 220,000-pound cars together at 5 miles an hour. The peak force of each impact speed is recorded to produce a summary curve at all the speeds that are tested. The performance of a friction clutch mechanism is varied velocity dependent, giving smoother performance at higher speeds. The energy inflicted upon the draft gear in this 5-mile-an-hour impact would take an impact of more than 14 miles an hour with the 27,000-pound drop hammer, showing that the published performance curves for draft gears are not indicative of the actual service environment. As we move beyond the early 1900s, the heavier equipment is producing larger forces in both yard impacts and over-the-road revenue service, and new equipment is being developed to mitigate this increasing amount of energy. Center-of-car cushioning isolates the forces felt by the sliding center sill of the car from the lading above it. The first commercially viable design was called the hydrant cushion, developed by the Stanford Research Institute for the Southern Pacific Railroad. The design uses a set of plates and the sliding draft sill squeezed between a set of pads and the main sill by a hydraulic cylinder. These systems dissipate a larger amount of energy with strokes up to 30 inches as compared to the 3¼ inch stroke of a friction draft gear. Designed for the 170,000 pound cars of the time, hydrocushion could reduce the impact forces at 10 miles an hour by 80%, which reduced lading damage losses by 96%. By isolating the draft sill from the car body, the forces of a yard impact are managed very effectively to protect sensitive lading. However, the lading of any car coupled to this system would not get the same protection. Center-of-car cushioning systems eventually phased out as cars got heavier, compounded by the long-term maintenance issues that come with a car body this complex. Into the 1970s, advancements in materials technology allowed for a redesign of the conventional friction draft gear. The unit still has a friction clutch, but the coil springs are replaced by a single polymer spring stack. Back to the M901E drop hammer performance curves, the stick-slip phenomenon still shows up in this style of draft gear, though it's not as pronounced when overshadowed by a stronger spring stack. The stronger polymer springs produce a noticeably larger energy capacity than the original coil spring data shown in gray, with significantly more force seen in the release curve as well. The next design evolution for cushion cars is a series of different, shorter end-of-car cushioning units. These cushioning devices have a small port in the front that's used to fill them with hydraulic fluid, which in modern designs is pressurized with the addition of some nitrogen gas. As the unit is compressed, hydraulic fluid behind the piston head is forced into a series of check valves through an outer chamber to the front of the cylinder. Due to the differential area of the front and rear of the piston head, the pressurized nitrogen will return the unit back to its neutral position over a minute or two. To keep these cushion devices from stroking continuously, the check valves in the internal housing have a level of pressure that must be achieved before they will allow any hydraulic fluid to flow. Different iterations of this design have been developed over the past decades with different preload and draft protections for different car types. Most recently, the ongoing concern continues to be with the level of internal hydraulic fluid and pressurized nitrogen gas. The unit condition indicator was added to the front of the unit to allow for external visual inspection of the unit while still in the car. This is necessary due to the noticeable fluid emissions out of the piston rod seal, though it cannot visually validate the proper functioning of all the internal valving. A hydraulic impact curve is similar to a draft gear impact curve, though they are very different in the mechanisms that produce them and the amount of stroke that is developed. The first phase of the curve still runs out free slack, though that can be more than 2 inches in the case of a cushioning unit before building up enough force to cause the check valves to open. Once the cushion unit begins to move, it will stroke smoothly until the impact has concluded or the unit fully compresses. Again, the cushion unit will return to its neutral position on its own over 1 to 2 minutes. This can all be seen in the impact video, including the 2 or more inches of free slack that exists within the system. Though there are different cushion unit capacities, they will generally go solid at 4 to 6 miles an hour, and are more violently snap back to their neutral position in revenue service due to in-train forces before they can ever return on their own. Along with the available stroke, this can have adverse effects on the life of the unit as well as the structure of the car. Like the summary curve of different draft gear impacts, the peak force of each cushion unit impact is recorded to establish an overall operational envelope. The maximum allowable forces for this envelope vary depending on car weight and available unit travel. This allows for different designs to be applied to lighter auto racks than would be required for box cars, coil steel cars, flat cars, center beams, and bulkhead flats. The freight rail industry is in a very different place now than it was over 100 years ago, moving longer, heavier, faster trains every day. The equipment required to accomplish this progress is not one size fits all, and we've watched as this equipment has developed and evolved to match the demands of the industry, towing the line between yard and road energy management for sensitive lading types. As this trend continues, new systems will need to be implemented to keep up with the goals of increased throughput and extended component life. With this in mind, Strato has developed the Selective Cushioning Unit with AAR conditional approval for open interchange service and 2 years of service data supporting an actively expanding install base, because Strato is in the business of moving freight, longer, heavier, faster. As I said at the beginning, my name is Jonathan Sundy. and I'm Strato's Chief Engineer for Draft Systems. Feel free to contact myself or your local Strato sales manager for more information on this project or any of Strato's other solution-oriented product lines. Thank you.